Hi there, my name is Tommy Wood. This is another video to try and help explain a little bit about some of the research that I've been doing into a specific system, which I've given the name SERD model. It's just because it's basically, it involves space elements, so it's space element reduction duplication model. And I'm going to start off just by giving a little bit of a recap. You might have watched some of the other videos that I did. I did one video just sort of giving an overview of the structure of the model, which you can have a look at. I did another video talking about the code that I was using and a little bit of visualizations of the system. And the other was some evidence that one of the embedding algorithms that I use satisfies Newton's laws, or Newton's first law. And I do have some evidence that suggests that it satisfies the other three laws as well. This video is going to be focused on a experiment that I did into this system, regarding whether this system obeys relativistic rules. So, for example, the Einstein's postulate, second postulate, or well, the postulate that the speed of light is constant in all inertial reference frames. This seems to me to be quite a fundamental test of any model. It seems to be quite a fundamental aspect of any space-time that is realistic or represents the universe in some capacity. So it's really important to demonstrate this. So essentially, we need a definition of an inertial frame in our model, and also light speed, or what light is traveling through the system. Okay, so let me just do a little recap. So the first thing is, in this model we have two main things. We have space elements and we have point particles, and these are the fundamental constituents of the system. And the space elements, they can duplicate. Okay, so that's where you have a space element. I represent a space element with a sort of dash, and it splits in two, and then you can also have a reduction, which is where your space element essentially disappears. And they have probabilities. So the model that I'm investigating, the way I'm investigating this model is not so much in a comprehensive, in a sort of exhausting all possible avenues sort of way, which is more like the Wolfram model, where you're exploring every single possible series of update events. What I'm doing is I'm taking a more statistical approach. So I'm assigning a probability to each update event, and then I'm running the system and getting a sort of a subset of possible paths, and then taking some statistical averages for that, and then trying to understand a bit more about the system. It does mean that I'm able to get a little bit further, I think, than if you sort of measure every single possible outcome. But it does mean that when you are doing large scales of, essentially I'm doing Monte Carlo loops, right? The more loops I do for a smaller number of time steps, the less accurate my system becomes, because there's repeats will occur, and also, the less loops you have, the less accurate it is as well. So then point particles, they can split and they can merge. I'm not going to go into this too much today, because we're mainly focusing on the propagation of information of the duplications and reductions within this system. But a split is where a point particle splits in two with a space element in between, and a merge is where a space element that's separated by a number of point particle that's separated by a number of space elements. All those space elements reduce in the same time step, and you end up with one point particle. You can possibly imagine that if a merge occurs, that the 2 point particles are sort of adjacent, but there's no sort of spatial division between them, or no spatial extent between them. And that's an interesting idea. And there are a bunch of ideas regarding how splitting and merging affects the system. So generally what the system looks like, a simple version of it, is kind of like a complete graph, but at first it was like a complete graph where every vertex was connected to every other vertex by what I call an interaction edge. And an interaction edge is simply just a string of space elements, and those space elements, as time undergoes, can undergo some update rules, and those update rules are basically just substitution rules where the space elements either duplicate or reduce. And then the information of the duplications and reductions then propagates through the system, much like a almost like virtual photons, right? They're propagating through the system, and when a propagating duplication sort of is on top of a reduction, they superpose each other and cancel out. And so, if you want to look at this a little bit more in detail, you can look at my earlier videos. Anyway, so we have this system, and the information is propagating through the system. You choose one of the point particles to represent the observer of the system, or the sort of the center of the system, and then all the information in this sort of local view of the system will be propagating either radially towards that point particle or non-radially. And if you have a non-radial interaction edge, that's an interaction edge that's not adjacent to the centralized point particle, it will go in both directions like this. And then once it gets here, it will update all radial and interaction edges to get to the centralized point particle. When I'm actually implementing this sort of local view of the system, the information on a non-radial interaction edge is just like an array of numbers. And a number could be, I do have a string representation of the system as well. There's a sort of string substitution version of it, so you can imagine each interaction edge is in a sense a string substitution system that then updates based on how many adjacent reductions or duplications there are on a vertex. But then also you can do it as an integer code where the integers sort of sum up. Anyway, so you've got this propagating information, and the information is propagating through the system, and it affects its nearest neighbor in each time step. Right, so if I have a space element here, and I've got, I don't know, let's say -9, the information is actually stored on the boundary of the space element. The next time step, it sort of propagates to the next space, and it will be sort of -9 there in the next one. But the whole system is undergoing this dynamic change as you go through time, and so the information is sort of being sort of shifted, as it were, in the interaction edge. Then in this system, I then embed it in a sort of Rn space, and there's various different ways I do this. Either I sort of do a strain minimization algorithm, so I'll just show you some of I won't go into too much details. I'll just sort of show you the algorithms, and then you can just sort of stop it and look at it. So this is the strain minimization algorithm. This just relaxes the state into a local minima for strain, and this is sort of reflective along the axes. This one is the one that I've been using, and I think it's the most natural embedding of this system. It's a time iterated embedding. It basically takes the state of the system, it takes a coordinatization of the system at a given point in time, and then the next coordinatization goes through this algorithm. It applies this algorithm once. It's almost as though the system is trying to find a configuration in flat space that minimizes the curvature of the system, but it's only able to get to it by one iteration in each time step, so it's never quite getting there, right? It's pursuing it, but it's not quite getting there. And the interesting thing about this algorithm is that on large scales, and even in smaller scales of the system, you can see that when you stop the updating events, the point particles tend to move in straight lines. They tend to just move at the speed that they were going at. They sort of they almost fall into an inertial reference frame, and this is where these correspondences seem to be occurring in the system. And I really want to get some feedback on that, because I think it'd be really interesting. The idea is that let's not look at that. The idea is that in an inertial reference frame, the things that are moving the system around are the changes in the sizes of the interaction edges, or the size of the interaction edge that the centralized point particle is aware of. And if you take away those, then essentially there's no force changes occurring on the state. and the particles tend to just move off in straight lines. However, because you're working in small systems, there will come a point where either it begins to relax into a minima state, or it gets to sort of the edge of the system and sort of gets pulled back round again and sort of starts to kind of have a little bit of angular momentum, or a little bit of sort of acceleration in a sort of circular manner. But what I seem to be seeing is that basically putting PD and PR to 0 has the effect of sort of putting this system into an inertial frame once the centralized point particle is essentially aware of that. Because remember, all of this information is propagating through the system. I'm just going to make a quick point about the splitting and merging on the side here. So splitting and merging in this system, if you imagine you've got a bunch of interaction edges and you perform a split, those interaction edges, what happens to them? You could say that they might get cloned, as in they sort of become copies of themselves. But what I've realized is actually the most natural sort of consequence is that the information of the split propagates through the system in the same way that when a duplication or reduction occurs, that information propagates through the system, and it sort of creates a bifurcation in the system. And this kind of leads to, I think, a much more interesting system, a much more interesting state, because it's not just a complete graph, right? It's a sort of dynamically evolving graph with many bifurcations in them, and these bifurcations may combine, right, and pass each other, in which case you might get something that looks a bit more sort of like this, right? And it's almost an interesting network of this system. Merges as well, I just want to make a little point about that as well while I'm here. Merges occur when all the space elements between 2-point particles reduce in the same time step. And if you imagine they've all got sort of incident interaction edges on them, what happens to those incident interaction edges? Well, it sort of makes a natural sense that these interaction edges would sort of form multi-interaction edges. And you could treat a merger as, possibly that these interaction edges become, this point particle just becomes 1-point particle. But you can also imagine a sort of internal, adjacency, sort of internal space almost, that has no size within the dimensions of the space that we're embedding within, because there's no space elements between them. But there's a kind of adjacency or separation in a sort of internal space, and that is an interesting idea that I think could lead to some possibly quite interesting dynamics, especially when we're considering merging and splitting of these point particles. These create multi-edges. Now, it's important to remind you that the definition of mass in this system is basically that particles that have mass, they, essentially fermions, they are clouds of splitting and merging point particles that have reached sort of an equilibrium, where the rate of splitting is equal to the rate of merging, and so overall the number of point particles in this cloud remains the same. The more point particles you have, the greater the mass of the system, because the more actions you need in order to sort of move this system, and to sort of the heavier the blob, the more massive it is. And that kind of makes a bit more sense, right? Because if you have an individual point particle, it's quite easy to move that individual point particle around the system. Whereas if you have a big cloud or clump of point particles, it's more difficult to do that. You need more energy. And an interesting consequence of this is that when you have more splitting and merging inside these sort of point particle clouds, then you're likely to have a greater number of interaction edges in multi-interaction edges, right? Because of this effect that when things merge, they also tend to merge the interaction edges. And you can imagine that you have these multi-interaction edges, and they somehow, I can see in a way how that would relate to affect the embedding algorithm. Now, there's also the possibility of zipping. That is where a multi-interaction edge sort of begins to zip itself up almost. So you sort of imagine that one, and there's maybe various ways in which this could happen. And yes, so there's that. The other thing is. So the other thing is that I'm quite interested in potentially for later investigations is how when you increase the number of interaction edges in a multi-interaction edge, you are essentially increasing the probability that one of those interaction edges is going to fully reduce in case of merging those 2-point particles. And I'm curious to know whether that might create an emergent attractive property on massive particles. It seems to emerge quite naturally out of it that the more massive a particle is, the more interaction edges there are in multi-interaction edges on those point particles. And if you increase it up to a certain point, then the probability that one of those interaction edges is going to fully reduce, and therefore merge the point particles, is increasing, right? I could do a little example of this. I'm going on a little tangent and not quite explaining, doing the relativistic stuff that I want to do, but I'll just explain it quickly. Imagine you've got one interaction edge. There's a probability that it's going to merge, but then let's add a bunch more, right? There's an increased probability that one of those interaction edges is going to merge. And once one of those interaction edges merges, the natural consequence is that all of those interaction edges become self-loops and then don't contribute to any distance between those 2 point particles. And then any point particles that were sort of connected to that are now pulled almost. So if you imagine, let's say we have sort of a particle here, particle here, particle here, particle here. Well, now there's this effect of sort of pulling these two things together, right? Because all of a sudden these particles, let's say this is a sort of particle here, right? They merge, and then all of a sudden these two sort of pulled in together, and I believe this would make a sort of attractive force. And maybe this is related to some kind of emergent gravity. I don't know, but it's interesting anyway. Okay, so back to the relativity, the postulate of special relativity. So I think a good place to start with this one would be just basically what I'm trying to do. Okay, so the postulate is that if you're in an inertial reference frame, the speed of light is constant, right? Now, obviously, you've got to remember in this system, this is a kind of multi-way system where there's duplications, reductions occurring, and it's quite fuzzy. You get sort of probability distributions, and everything's a bit sort of zigzagging around, and the motion of expectation values is sort of a bit zigzaggy. So it makes a bit more sense that we're not sort of talking about the speed of light in the sort of microscopic view, because in the microscopic view it's very non-deterministic and very noisy, and so it's likely that you would get kind of crazy speeds for this sort of noisy system because these point particles are zipping around. And you can imagine that's almost like if you imagine that you have an electron and you are actually able to see where the electron is all the time, and you're not really measuring it in an inertial frame because the electron's sort of doing this sort of jumpy business in quantum mechanics. I mean, there is evidence that suggests it's a more continuous motion, but there is still sort of a quantum jump or a quantum leap that it does. And so connecting that with the sort of special relativity idea of strict speed of light being constant in inertial reference frames all the time. I mean, these particles aren't really in themselves in inertial reference frames. So point that I'm making here is that it makes a bit more sense to talk about the average speed, right? The average velocity of these this propagating information. So how do we do that? So the first thing that I did was a little bit naive, I think, in hindsight, because we've got this system, and you know, I've got an array of numbers here, you know, and it's propagating in this direction, and I can store all the numbers. Basically, what I did was, I think maybe I didn't really know exactly the right way to do it initially. I assigned to every number. Well, let me show an example. Actually. Okay, so you probably remember seeing this from an earlier video. This is the evolution of a single microstate path of one interaction edge. So this is happening between every point particle in this system. It's important to, in the experiments that I've been doing to test the constancy of the speed of light in all inertial reference frames, I've not been doing splitting or merging, and so as a result there's just one interaction edge between every point particle. But there's essentially this system, and you can see here we get these sort of clusters of information forming, these little packets of essentially energy, little energy packets that when they update on the centralized point particle, they inform the centralized point particle that an action or duplication or reduction has occurred. These are what I think are kind of like virtual photons. I mean, they sort of behave in a similar way, and they propagate through the system. Now, they affect every space element next to it in each time step. So it does sort of feel quite intuitive that the speed that these wave packets would, or I call them wave packets, they're not really waves, energy packets, or information packets, travel at would be one space element per time step. So in the interaction edge case, single interaction edge, if we treat it as a sort of one-dimensional space, then that's kind of the case. That makes sense. But when we start embedding this system in higher dimensions and using this system in a sort of coordinate space, it's not immediately obvious that that would be true, right? Because that would be affected by the embedding algorithm. I mean, I've done embedding algorithms where I've done experiments on this where you get crazy values for the speed of these particles. And so the first thing that I did was a bit naive. What I did is I just said, okay, well, let's just assign a tag to each point particle that allows us to work out where its location is in the interaction edge, and then use that to determine a position in space, and then sort of work out all the instantaneous you know what, I'm going to take you through the whole process of how I did this. So the first thing is so you've got this array of numbers, you assign to every number. It was quite a labor intensive algorithm, but you have 2 point particles, you call it pp4 and pp5. The reason why I'm using pp4 and pp5 is because when you're embedding in 3 dimensions, you need 3 point particles, 1 point particle for the centralized point particle, 1 point particle which defines the origin, the other point particle for defining the x-axis, and the other point particle for defining the xy plane, and then all the other 2 particles are essentially free. They're not constrained, right? So this is pp3, and this is pp2. This is pp1, right? And so that's why I'm experimenting it with 5 point particles, because otherwise I'm putting constraints on the other point particles to be within the plane associated here. By the way, just a little note here, because there's no splitting and merging in this system, whenever an interaction edge fully reduces, the effect is essentially that it just instantaneously splits again. So you never really get any problem with multi-interaction edges or bifurcations or splitting mergings, and none of that stuff. We're not dealing with any of the splitting and merging. But we have this system, and we have these propagating information wave packets. So if I just draw the lines here, I'm only going to draw the lines between point particle 4, 5 and point particle 1. And you imagine here, just like in the example I gave you before, right? Each one of these is a number, right? The negative signs tend to be the blue, and the positive signs tend to be the red. Negative signs tend to create more clusters, the red duplications. Just a little note: there is a connection here to the idea of time dilation that was proposed in the Wolfram model, because when you increase the duplications, you have the effect of essentially slowing time down, because the information will only reach the update vertices or the centralized vertex at a slower rate. So your observed view of the system is kind of slowed down, and I think that there's some correlation here between that and the expansion of space. The fact that when we look at galaxies further away, they are propagating. We're looking at them further back in time. Time is sort of moving slower if we're looking at a clock on one of those galaxies, and it might also suggest why all this energy is coming out of nowhere, because it's just energy that we haven't yet observed yet from the expansion of space. So there is a sort of idea there. Okay, so we've got this system, and it's kind of dynamically evolving. We've got a bunch of different action wavefronts that's sort of propagating through the system. My first approach was to just assign a value that basically tells you what fraction. Let's call it lambda t, right? And we applied this value. It's a fraction that tells you how far along this interaction edge this wave packet is. And then I worked out sort of all the incremental velocities, and then I sort of averaged them. That didn't really work. I thought I got, it didn't work because I wasn't considering that the state of the system is defined by the observer, and the observer in this case is the centralized point particle. So I can only really define a position in space from the point of view of the centralized point particle. Basically what I'm doing is I'm using the global system, the God view, to define these velocities. The other thing is these wavefronts, they're propagating through this system, but the system is evolving instantaneously. So what I mean by that is if you imagine we have an interaction edge with all the space elements, I've got a wavefront here. It's possible that like a third or 3/4 of these space elements all duplicate, and then you've got this space, this distance here, right? And this wavefront's trying to propagate. It's suddenly shifted from here to here, isn't it? Right, in one time step. That's just one time step. It's shifted from there to there, and these point particles, they could be quite far away, right? So it feels like it's very non-relativistic, this way of seeing things. So I shifted from treating these, trying to measure the sort of incremental velocities of these waves, and I moved to actually the light clock measurement. Okay, so the light clock measurement basically is like this. Imagine you've got 2 point particles. You got your centralized point particle, and then of course you got your frame of reference defined on them. And this is all a bit messy. Let me just put it. There we go. You got your frame of reference, and what we're doing is we're saying, okay, at one point in time, let's call it t1. I'm sending a light pulse from point particle 4 to point particle 5. It travels along the interaction edge and gets to point particle 5. Okay, and that hits it at t is equal to 2. Now I can't just do this from the God view, from the global view, and just take those values, because who's aware of those values? Who's been measuring those values? Who's the observer, right? Well, the observer is the centralized point particle, right? So we need to define the paths that the information takes, and then use that to derive the times. Now, when I'm saying t is equal to 1, t is equal to 2, I have to enforce the system to be in an inertial frame. And like I said before, there is the correspondence between information and energy and force. And so an inertial frame is a frame where there's no force. So it makes sense that at least at the scales that we're working in, on the larger scale, we might be able to get a sort of an averaged inertial frame. So there's still sort of microscopic forces working, but overall the system is in an inertial frame that could work on a large scale. On a small scale, we don't have that liberty because we can't describe a large cluster of particles. We can't describe a large system. We can't describe. You could imagine that every little bit of information that gets updated on the centralized vertex has a much larger effect on a smaller system than it does on a really big system, right? So if we're trying to average it, those fluctuations that we get as a result of the incident information are too large. To really define what it means to by an inertial frame. But in this way, I'm seen to have quite a bit of evidence to suggest that this is the way to describe an inertial frame. Mainly because when you do this, the velocities do this. They tend towards a constant value, and the accelerations do this. Right? They drop down to 0. They drop down to 0. In fact, actually, if you carry on with this and continue on, what actually happens is and it begins to sort of wiggle about and start doing lots of stuff after a while, and that's because it's a small scale system, and the same happens obviously for the corresponding accelerations. So this is the velocities and this is the accelerations instantaneous. So how do we describe this? The first thing is we imagine that we run the system. Let's rub this out. We run the system from a union state, right? So normally the initial state of the system is just a union graph where every vertex is connected to every other vertex by a single interaction edge, and there's essentially no information stored within the interaction edges of the system. All of the effective edge weights are just 1. The effective edge weights are the weights or the sizes of the interaction edges that the centralized point particle is aware of. So from this union state at t is equal to 0, I mean, you could imagine the union state just gets created by a point particle splitting, but without any duplications occurring, right? And so you get this sort of very simple state. For 3 point particles, it might look like that. For 4, it might look like that. For 5, it's just a sort of unitary complete graph. And we evolve the system. Like I said, if a merge occurs, it just splits instantaneously, and we evolve the system from t is equal to 0 up to t1. Right? So we imagine that we have this t is equal to 0, and we evolve the system up to some value t1, and we can have that to be any specific value. Be 1 time step, 100 time steps, 1,000 time steps, 1,000,000 time steps. Who knows, right? It could be anything, right? And we run it. Now the idea is that we run it 1 time step, and then later on, once we've sort of described this way of doing it, we will then do a loop over this on many runs, and that will give us an average of the velocities. But at t is equal to 1, we put our system into an inertial frame. And what I mean by that is we fix the probability of duplication and the probability of reduction to be equal to 1. Equal to 0. And that means that all of a sudden no duplications or reductions occur. What does this do to the system? Well, the centralized point particle is still not aware that the system is in an inertial frame, really, because all of the information is still propagating through the system and updating the system, and that will effectively create effective forces on the point particles. So what we have to do is we have to wait for this centralized point particle to essentially become aware the system is in a inertial frame, and we do it like this. So first of all, when we fix the inertial frame, that's going to fix the number of space elements between these 2 point particles and the centralized point particles. So we can give them names. We can say this is S45. We could also call it S54. It depends which direction we're going in. It's be on a matrix, and we could call this one S41 and S51. So let's rub these out because this is confusing because I've got these different times here. So if we were to start imagining that we had an event on PP4, and what we're really doing is we're imagining, okay, what's the time it takes to get to the centralized point particle from this direction, and then that will be the time that we start. The only problem with that is that it's still not an inertial frame, because if we imagine, okay, if we imagine that T2 is equal to T1 plus S1 S41, well, all of this information still has to propagate through PP4 and then propagate down to the centralized point particle. So that's not going to work, because by this time the system will still not realize that we're in an inertial frame. So what we need to do is we need to wait a little bit longer, right? So the way to do that is to define T2 to be equal to T1 plus S45. That's basically the time it takes for all the information that is on in the interaction edge between point particle 4 and point particle 5 to pass to point particle 4. Then, when we imagine the time T3, the time T3 is the moment that this point particle here, the centralized point particle, becomes aware that the system is in an inertial frame. Okay, and that's when all of the information that's propagated from PP5 to PP4 and then down from PP4 to 4.1. Now, that's not saying that there's not other information that might be out there, but it's at least saying it's an inertial frame with respect to these 2 point particles. Okay, other point particles might still move, but that will be a sort of decaying effect, most likely. And so we can define that. That would be T2 plus S41. So that's the time that the first event occurs, and then we, that's essentially the start of the light ray, right, in a sense, going from here to here. So we define a position in space-time, well, a position in space really, of point particle 4, and we define it at that time, and that's the start where the centralized point particle is aware that's in an inertial frame, and that's T3, and then we can imagine that as X4. It's what, T1 plus S45 plus S41. Okay, so that's the first moment that it realizes that. Now, we also want to work out the time it takes to get to PP5 and what time that would be where the centralized point particle becomes aware of it from that perspective. So we're going to want to work out another position, and that's going to be another time T4. T4 is the time it takes for the light to reach PP5 in the global frame, and that is equal to T2 plus S45, and then T5 is the time it takes for that light, for that information, then to reach the centralized point particle going down directly from PP5, and that would be T4 plus S51. Remember, these space elements are not duplicating and reducing, so we can just add the time. So it's sort of time is space, and space is time. Okay, so then we can then define the moment that this point particle is updated and is the centralized point particle is aware of it, is x5 t5, right? And that would be x5 t. Well, we can write this in terms of t1, really, can't we? So it's t1 plus 2s45 plus s51. Okay, so now we've got these two times, right? We've got these two positions in space and time. And so then we've got the distance that is travelled, and then we've also got the time difference, right? So we can work out a velocity, or an effective velocity, of this wave particle, or this information propagating through here, as being x 5 t5 minus x 4 t3, right? And then we take the norm of that and we divide it by the time difference. So that would be 2 t3 t5 minus t3. You might think, okay, well, there's a little bit of a weird thing here, which is that we might end up with a negative velocity, because it's possible that this information reaches the centralized point particle from point particle 5 before the information reaches it from point particle 4. It's because the system is largely non-Euclidean, and you could have a really long S4, S41, and a really small S51 and S45. Interestingly enough, you can actually work out that this only happens when the triangle inequality is violated, right? So if S45 plus S51 is less than S41, then this leads to a negative velocity. What I've done in my measurements, because I'm just interested in the speed of the light, I've actually just taken this negative velocity and I've taken the norm of it, the absolute magnitude of it, and then put that into my calculations. Someone might think that's not a very sensible idea, but I get some quite interesting results as a result. Okay, so I'm not going to go into. So first of all, let me show you some of my results. So this was when I did the global states of the system. You get some high velocities here. I'm not going to go into this because this is when I was doing it not in the correct way. I got some quite large velocities. This is when I was forcing it into an inertial frame, and I was again looking at the velocities in the global state, not in the observed state. But it still was quite interesting results that, when you forced it into an inertial frame, it tended to go down towards 1. I also looked at sort of average values instead of taking instantaneous velocities, working out the position of the velocity at a given point and then averaging it. But this, again, it wasn't taking it from the point of view of an observer, which is what we're doing when we're considering the updated the time that the information updates the centralized point particle. So it took me a bit of time to sort of get to the correct configuration for this code for this experiment, and then this is where I started doing it. So if we actually have a look at some of these code, one of the interesting things is that you could get a value, and it may not be. I mean, obviously, what we're looking for is a constant value that is always the same, but it would be implied that the value would be 1, right? Because 1, that would make a nice kind of correlation to the Planck length and the Planck time, and the values of the space elements of length. And also we have 1 space element per time step that we're propagating through the system, so it sort of makes sense that would be the value. So we're looking for a value that tends towards 1. The difficulty here is with there are some parameters that may change. So, for example, the size of the system may change. That can be varied by changing the time steps. If you increase the probability of duplication, that does grow the system, but it grows the system exponentially, and that leads to computational problems later down the line. I mean, the amount of time it takes to code a system and the amount of memory required in order to do that with probability of duplication being greater than probability of reduction is huge. So we can't grow the system like that. We grow the system by keeping the probability of reduction and duplication the same, and then just evolving it over a greater length of time. The longer the length of time, the greater the chances are that it's going to grow to a larger size. So there is a correlation between the scale of the system and the time that the system has been there. So we're looking at some parameters being the scale of the system, or the time that it takes for the system to evolve, and also the number of point particles, because I'm fixing the number of point particles in this system. Generally speaking, I take the probability of duplication reduction to be a third, because I think that nicely works a bit more. That works better with the idea that, you know, a multi-way system, each update event is sort of equally likely. But I do sometimes use 0.25. I don't know why. You know, that sometimes happens. Anyway, so here's an example. The median you can see here is quite close to 1. It's not exactly on 1, of course. And then the blue line here represents 1. And this is for m is equal to 8. As we change the parameters, we might increase ts1, which is the time that the system has been allowed to evolve. And we get values of here. Actually, I am not considering the negative velocities to be normed, okay, and or absolute values, and that's what I start to do here. You can actually see if you go up. Oh, we don't have those values there, but you can see that some of the velocities are negative, and that's as a result of the triangle inequality being violated, and you end up with this sort of time reversal. So I then take the norms of these values, and we get a variety of different values that sort of tickle 1. They're sort of around 1, but not quite 1. So what I then did was I took a mean or an average over that, and so for each of these, we have a certain number of runs, and you can look at this information here. So m is the number of point particles. TS1 is the amount of time that the system has been allowed to evolve. This is just defining the point particles, the dimension that we're embedding in. This is defining the inertial frame, right? So that's defining when the inertial frame occurs. And this is just defining TS2. So we set up the initial system, and that's how many times we do the runs. And we do a certain number of loops for calculating the speed of light. So right, so let me then explain how this works. So we're taking a number of runs. The runs, let's say there's 25 of them, right? And they all go up to t is equal to 1. Then from there's a number of loops, okay? And these loops are run. There will be a point within that loop where we fix it into an inertial frame. So we're basically allowing there to be some additional loops before we get to the inertial frame, and then at that point it's fixed to be an inertial frame, and the whole system is allowed to relax. So at some point, and there'll be a different point for each one of these runs, the centralized point particle is updated that it's in an inertial frame, and so the larger we make this value t2, the more accurate our result. And also it sometimes leads to errors where the system doesn't sort of get into an inertial frame but that's not that won't add to the average values of the velocities. So for each one of these runs, we take a sort of average of all the velocities. By the way, just to go back, once we've worked out the point at which the inertial frame is affecting the centralized point particle, we can then work out those values for every sequential time step. So what I mean by that is we would do V is equal to norm of x t5 minus, so x5 t5 x 4 t3 like with the other one, divided by the time difference, or let's just call that delta t. But then we can also, let's call that v1, but then we also have v2, which will be the moment after it, the light that passes just the moment after it, still in the inertial frame, and that will be t5 plus 1 minus x 4 t3 plus 1, and again that would be divided by delta t, and it would be all normed. That's to account for the negative values as a result of time reversal symmetry, or time reversal. But we're just interested. So basically, every individual loop within each run will have a series of velocities. Each one of them will just be, so we could call this I, and it would be x5 t5 plus I minus x4 t3 plus I divided by delta t. And again, just to remind you, t5 is the time that the centralized point particle becomes aware that the information wave packet reaches the point particle 5, and t3 is the time that it is aware that the information left pp4, right? So we're sort of imagining we send off this pulse and it reaches pp5, pp4 is here, pp5, and this is x x4 t3 x4 x5 t5. Okay, and that just stems from a little bit of this algebra here. Okay. And so when we do this, we're taking a bunch of these are the runs, and so runs will result in different initial states, and these are the loops. Okay, and so we get various different runs. We in the simulations that we've done here, we've done 5 runs, and what we're doing is we're basically just averaging over all runs. We're averaging the values over all runs. So, and we're also storing as an array, as a big array, all of the individual velocities that are measured when it's in the inertial frame, or when the system becomes aware that it's in the inertial frame. So let's take an example here. So this is, oh no, not this one. Is it this one? Here we go. So this is an example. So we run it, we output the average velocity, but what we're doing here is we're actually storing all of this information in an array. The average value we get at the end, we put in m is equal to 5, and we do 500 time steps. The average value we get is about 2. But then again, if you just look at this is the distribution of the velocities in the inertial frame. There's a huge range of velocities for these values, but a tiny interquartile range that sits within 1. Now the other thing is, and this is true for different values as well, you can see here, if we this is for a smaller number of time steps, and a smaller number of time steps still, 100 time steps, how that affects it. Now we can also look at this example. Now, the other thing is that in the other examples, as the system grew, the velocities grew with them, and I wanted to show that there was no scale dependence on these velocities. So you would imagine if the system's really big, maybe there's quite a lot of large velocity that these point particles move around at. I wanted to show that there's no real correlation between the scale of the system and the speed at which this sort of imaginary information packet is traveling at. And so I store as a bivariable basically the scale of the system and the average velocities, and we get sort of a distribution that looks something like this. And you can see that it doesn't seem to change that much. It doesn't seem to be any correlation between the scale of the system, the average scale of the system, and the average wavefront speed. The average scale of the system is calculated by just taking all of the instantaneous edge sizes and just averaging them all, and then averaging that over all loops. So here we have. Now I wanted to see what the difference was for essentially increasing the size of the number of point particles in the system for a small number of time steps, and so we did for 5, and we get we get an average quite close to 1, and we get a median sort of again interquartile range here. Now and then if I increase 8 to 8 point particles, we go down. We get I think. By the way, when these errors occur, that's just because the point at which this centralized point particle is updated, it goes beyond the time steps that we've allowed to observe the system. Here again, there's no correlation between the average scale of the system and the wavefront speed, and again, the average speed is about 1.2. So you can see the speed, the wavefront speed is going up a little bit, and then we did it for 13 time steps, and we can see that the median gets close to 1, the mean goes up, and I did this again for 20 time steps, not that much different, but yeah. So you can see here we've got. The mean goes up a bit, the median again, but really the sort of the point to make here is the values are very, very close to 1, and this is in the inertial frame, and when we look at something like this. Like, it seems pretty crazy that these values are so constrained to be around 1 in this distribution. It's a very, very strong skew to 1, or fixing to 1. And I think there's evidence here to suggest that as you increase the number of point particles and you increase the scale of the system, that actually this system tends to the velocities in the inertial frames tends to 1. Okay, that was quite a long video. I think I'm gonna stop it there. Okay. Yeah. So that's the results that I'm getting. I'm gonna hopefully write up a paper at some point soon. I'm also happy to share my results with anybody who is interested and would like to see them. And if anybody has any comments or questions or would like to get in touch and talk to me about some of the stuff that I'm doing, I'm definitely keen to get involved in some collaboration. Okay, thank you very much for listening, and I'll see you in the next video.